So mainly you can see in the scattering, we have to solve the all this Schrodinger wave equation and all this scattering cross section into a spherical polar coordinate, and which is really tough to solve completely. So we have make different type of uh, tricks. So these all are different tricks based on observation, that we can have a different way to solve this particular scattering problem. And you can see that bond approximation is quite successful approximation, which can give you exact answer which is resemble with the experimental result, such as we have verified it for Yukawa potential as well as Rutherford scattering. And the thing is more or less match with the experimental result. So in that process, we have one more uh, theory, or I am not saying it is trick. So this is analogical theory. This is derived from one dimension, and then once we have derived it from one dimension, we can just analogically apply it onto three-dimensional system. And this method is identified as phase shift method. And obviously the real challenge is finding the amplitude part, isn't it? The f theta, and which f theta is AL, and this AL is partial wave amplitude. So this is real challenge. So we have to just try to figure it out how we can get all these things. So here is one more way to solve the basically scattering problem. Sorry. So let's first go for one-dimensional analogy. So because we can understand physics from one-dimensional analogy, then we will implement on three-dimensional thing. So let's go for one-dimensional analogy. And what is this one-dimensional analogy? At x is equal to 0, we have infinite potential, and up to some a, we have some function of potential where Vx is equal to not 0. So this is at distance a, and this is the basically form of potential. And so this is area of this is area of scattering, and in this region we have potential V is equal to 0. So you can identify this kind of situation we have. Why we have taken at infinity here? Because in the spherical polar coordinate, we have from 0 to infinity, isn't it? So why we just try to match the all thing from spherical polar coordinate. And this is my potential Vx is equal to 0. So what will happen? I can throw particle from here. It will come here, and obviously its form will be changed here, and again it will go into this, it will collide to this wall, and again it will come back. So obviously whatever mathematics we can do in this region, here we have lot of mathematical challenges, because we don't know what is actually form of potential, and if you know also form of potential, then it is very difficult to solve it in a complete way. So what we can do? So obviously we have in this region we have my potential, we have my wave function something as phi x, and this value is basically, let's say this is function of sine kx, something like phi x is equal to sine kx. And this potential is very small range potential. Basically, this range is very small range incomparable to this one. So we assume that we can take this one approximately solution, not exact solution. We can take approximately solution into this range is sine kx, because we assume that if this thing will be very small, then my wave function must be decay at x is equal to 0. And we have sinusoidal wave function here because my potential is 0. You have either sine function or cos function, isn't it? है ना? So this is your basically a wave function into this region. What I can do, I can see physics into this particular wave function. So what is this thing? I can write 1 upon 2i e to the power I kx minus e to the power minus I kx. So this is my sine kx. So actually I have this wave function, and we can see what is my e to the power I kx wave function. This is incoming wave function, isn't it? This is incoming wave function. And what is this wave function? In this region, you have incoming wave function as well as outgoing wave function, because after the collision, your particle will be also come into this region. So you have incoming wave function and you have outgoing wave function in this particular region. Now, what will happen after your wave function is going to interact with this potential? This is very interesting. And my complete wave function is nothing but incoming and outgoing wave function, which is phi x, plus whatever happened to this particular wave function is your scattered wave function. Are you getting my point? ये समझ रहे हो क्या मैं कह रहा हूं?
Yes, sir.
Now, just tell me which wave function you can control, this wave function or this wave function?
Incoming one.
Incoming wave function you can only control. What will happen to outgoing wave function? Obviously, one wave function will be something like this. But what will happen outgoing wave function due to interaction of this, we cannot control. So the complete wave function psi x, according to concept of partial phase shift, we have just going to make a trick. And what is this particular trick? The trick is my complete wave function, not scattering wave function, my complete wave function psi x is equal to 1 upon 2i. Incoming wave function will be always there. So you cannot avoid this thing into this region. What I am going to change, I am just trying to say that amplitude of wave function is not going to change because probability is going to conserve. The energy of wave function is not going to change because we have conservation of energy. So throughout we have same value of energy. So I can claim that when particle is coming after interaction into this region, it can going to change with some phase shift. The phase can be changed. We are just assuming that this kind of situation. And what will be this phase shift? So this will be, let's say, minus sign. And we have to changing. So after the scattering, we have to only change into this particular outgoing wave. And what is this outgoing wave? This outgoing wave is, let's say, I kx, and there is some change in phase, and this is 2i delta k. Why I have put in 2i? Due to this mathematical compulsion, nothing else. You can put delta also, then your answer will be little bit different. But in general, every book, every faculty have taken this thing as 2i delta k. Okay. So this is, so there is some phase changes into this particular thing. So now look at what is going to happen. An amplitude for both incoming as well as total wave function is exactly same. So now we can have complete wave function, and in this complete wave function can be divided into two parts. That is your incoming and outgoing wave function plus a scattered wave function. So this is all about, we just want to write what will be my scattered wave function. So if we are going to compare it, then what will happen? We have A upon 2i e to the power ikx plus 2i delta k minus e to the power ikx must be equal to A upon 2i so I'm just removing this thing. So what will happen? A upon 2i e to the power ikx minus e to the power minus ikx plus psi s. And this is my scattered wave. So this plus this is equivalent to this one. This is complete wave function. And this, sorry, this is minus sign. So this is incoming wave. And here is incoming wave, but plus some changes. Sorry, outgoing wave plus some changes. So this is always we have this kind of situation. So what will happen? This and this will cancel out. And obviously, this thing is also cancel out, isn't it? This thing is also cancel out. We have psi s. And what is my psi s? We can get psi x as e to the power ikx into e to the power 2i delta k minus e to the power ikx. So what is my scattering wave function? Psi x is equal to e to the power ikx, and you have e to the power 2i delta k minus 1. And if I can write this particular thing, e to the power ikx, and what is this thing? I can take e to the power I delta x as common. Sorry, 2i will be not cancel out. Sorry. Because this is psi x, na? So this 2ix will be not cancel out. So a upon 2i will be there. Sorry. A upon 2i will be there. Because there is not 2a upon 2ix. So this will be remain there. So we have this particular thing. A upon 2i is also there. Okay. So we have a upon e to the power ikx delta x upon 2i, and you can take e to the power I delta k, thus delta k, minus e to the power minus I delta k. दिखाई दे रहा है?
Yes, sir.
है ना? So what I can write this particular thing? So I can write this particular thing, psi s is equal to, this 2i will go there, and then we have a e to the power ikx e to the power I delta k, and that value is what? Sine delta k. है ना? So this value is sine delta k. Now this is our scattering wave function. Now you can understand why we have taken 2 here. Why we have taken 2 here? Because it will just give you the phase shift in term of delta k. So delta k is phase shift, but we are taking 2i delta k such that we can write all this thing. So now look at here. Can you please tell me what is a to the power I kx? Just tell me what is a to the power I kx?
Outgoing one.
हाँ बताओ बताओ क्या बोल रहे थे? What is a to the power I kx? यहां से देखो, just from here.
Yes, sir. Outgoing.
Outgoing wave function. Okay, so this is outgoing wave function, and obviously this part is nothing but equal to your phase part. Okay, so the scattering wave function is outgoing wave function including some function related to phase part. That will be function of delta k. So this is the whole story for one dimension. Let us try to go for this whole story into into 3 dimension. Now, just tell me what is into 3 dimension. My total wave function into this region is phi x plus psi s. What is phi x there? What is phi x there? याद करो जब हमने शुरू किया था अपने प्रॉब्लम को करना तो. Just tell me what is this phi x there in the 3 dimension? Okay, what is this phi x?
Sir, ये e to the power I k dot r हो जाएगा.
What is phi x? Phi x याद है? The psi x is nothing. We have e to the power I kz plus f theta e to the power I kr upon r. याद है ये? यहीं से तो शुरू किया था.
Yes, sir.
है ना? And this is just r. And don't worry, here is in this z there is r itself is there. ये हम दूसरी बात कर रहे हैं कि इसको कार्टेशियन कोऑर्डिनेट में लिख रहे हैं, इसको स्फेरिकल पोलर में लिख रहे हैं. When we are writing it into a spherical polar coordinate, then p theta will be also there. Are you getting my point?
Yes, sir.
है ना? Now, if you are going to compare it from this to this, now can you please tell me what will be this phi x here? बताओ. आराम से, आवाज नहीं आ रही है. What is phi x? This one is your phi x, isn't it?
Yes, sir.
So this one is your phi x. So in this wave function, you have incoming wave plus outgoing wave. This is nothing but the superposition of incoming plus outgoing wave. With this analogy, what is phi x? Phi x is something like sine kx, and this is nothing but the superposition of e to the power I kx minus e to the power minus I kx at some amplitude a by 2a, isn't it?
Yes, sir.
So this wave function is basically incoming as well as outgoing also. Are you getting my point? So can I write this wave function as, so now look at, now you can see what is meaning of incoming and what is meaning of outgoing. Now it is not that only particle is coming like that. Okay, you have this central potential and your particle can coming like that. Are you getting this thing? So this is incoming. Okay, so this is incoming, and it is different thing that for one particular case you are taking this as your z axis. Suppose this is your central potential, how many ways you can approach this potential? You can come from here also, you can come from here also, you can come from here also. So you are coming all the way, and after then you are just going like this. Are you getting my point?
Yes, sir.
So when you will see the mathematics in a very nice way, then this function can be written as incoming wave and outgoing wave, something like we have written here. Something like sine kx. Are you getting my point? So let us try to go with this particular mathematics. Clear hai ye?
Yes, sir.
Yes, sir.
Okay. And what is this scattered wave? This scattered wave is nothing but this one. It is different thing that we are just saying that particle is coming in the z direction due to our mathematical compulsion. At some time you have to fix some direction, na? But what is happening actually? Actually your particle is coming from all of the way, from just coming like this, and after then it is just going to scatter. Okay, this is the thing. So let us try to go for writing all these things. So what is my incoming wave? Now I think you should understand, and this is very intuitive. This is very intuitive. Okay, and here mathematics works wonder. है ना? So what we have incoming or phi x or phi r instead of phi x, and this value is basically I can write a 2l plus 1 pi kr, sorry, 2I kr. Okay, and we have exponential I kr minus 1 to the power L exponential minus I kr, and this value is PL cos theta. Now, what is this particular wave function? What is this? What is this all thing are equivalent to? बताइए. Now we have done it. हम लोगों ने इसे कर रखा है. We have written e to the power I kz as e to the power I kr cos theta, and which can be proportional to, you have seen JL kr PL cos theta, remember?
Yes, sir.
And what is JL kr? This is some function of sine. Are you getting my point?
Yes, sir.
And now you can see there is function of sine. So this is somehow approximation of JL kr. And now you can compare it with your this particular thing. You can compare it with your one-dimensional thing. Okay, so this e to the power I kz I can write into this way by using my mathematics of spherical vessels function. And obviously this is in the region where you have free particle. So whenever you have region in a free particle, your answer will be a spherical vessels function. Don't worry, I kz is in basically Cartesian coordinate system. When we are transforming it into a spherical polar coordinate system, that means we are talking about this thing. Are you getting my point? So e to the power I kz is actually incoming wave and superposition of outgoing wave. Yes? In a spherical polar coordinate, not in a Cartesian coordinate. Are you getting my point? And we are just talking about all possible theta here. So it can come all possible theta. So this is your incoming and outgoing wave. This is your e to the power I kz. It looks like just going like this in a Cartesian coordinate, but in a spherical polar coordinate, it look like this. So you have to appreciate this thing. Are you able to appreciate this one?
Yes, sir.
And obviously there are summation sign, but we are comparing one L to one L. Okay, each and every L is going to compare. Okay, because you know that what is my total scattering cross section? My total scattering cross section is 2L plus 1 AL mod square L, and here is 4 pi. You remember this formula?
Yes, sir.
And this is if I calculate all possible L is equal to 0, L is equal to 1, L is equal to 2, then I can write this particular thing. So I am just writing it one particular L. So similarly, we have n number of L here such that you can use it. It's a so beautiful formulation. So now, what is my total wave function? Psi r. What is my total wave function? This plus a scattered wave function, isn't it? And from the theory of phase shift, what is my total wave function? So from the theory of phase shift, I can, which is going to change, incoming or outgoing? Which are going to change? Bataiye. So psi r is going to change a 2l plus 1 2i kr. Yes, this part will remain same, but because once you will fix incoming wave, it will again remain incoming wave. But after the scattering, you don't know what will happen to this one. It will just like this? No. It may be change in a different way. So but your K will remain same, your amplitude will remain same. What is going to change? The change is just only phase part, that is 2i delta k minus 1 L exponential minus I kr, and this is PL cos theta. Now, from one dimensional analogy, I can write, and you can also prove that psi r is equal to phi r plus psi s r. So from here, we have exactly same thing like one dimension thing. So what will be my psi s r? बता सकते हो क्या होगा? First of all, what is my amplitude part? Amplitude part is a 2l plus 1 for the given value of L, and that value is by this value. And what is my outgoing? And this is what? This is what? Outgoing or incoming? Which wave is there? Just tell me.
Outgoing.
Outgoing wave is there. So what will be this? So this will be exponential IKR upon KR, because 2i is also there. So 2i तो इसके अंदर आ जाता है ना? इसके अंदर, sorry, इसके अंदर आ जाता है. Remember? And this part will be again remain same, e to the power I delta k, and you have sine delta k. So just from there, I can write this my psi s scattering. Now, what is a scattered wave? This is your scattered wave. You remember all this thing? And this scattered wave can be written as 2l plus 1 al HL1. याद है ये? लिखा था हम लोगों ने? One
Yes,
type
sir.
Hankel's. And for the greater value of L, sorry, for the greater value of R, this HL1 is going to compare to, so I'm just removing this part. चलो यहां लिखता हूं, है ना, रहने देते हैं इसको, cos theta. This HL1, you remember it is e to the power I kr by r. Yes, है ना?
Yes, sir.
Okay. And AL is also, so there is HL1 is e to the power I kr upon r. So now, if we are going to compare with this one, if we are going to compare to this one, this particular thing, then this is equal to A 2L plus 1 AL, and we have e to the power IK upon r. because there is 1k is there, so the 1k is cancelled out. So now from here we can easily compare what is value of e to the power, what is value of al, because once you will get what is value of al, you can use this formula, है ना? So this a and this a is cancel out. This 2l plus 1, this 2l plus 1 is cancel out, and e to the power ikr is going. So what is my value of al? So my value of al is given by, we can have e to the power I delta k upon k sine delta k. This is your value of al, and now we can put this value in here, then we can have one particular formulation. So we can have sigma here. So इसको हटाऊं, and this value is, so this value sigma is equal to, I think, 4 pi upon k square and summation over 2l plus 1. And what is mod square of this one? What is mod square of this one? क्या होगा mod square? K square तो यहां लिख दिया, ऊपर वाले का mod square क्या होगा?
Sin square delta.
Obviously this is sin square delta k. Now you have this particular one more information, है ना? So एक साल एग्जाम में आया भी था, विश्वास ने दिया था क्वेश्चन. नाउ विश्वास, आर यू देयर?
Yes, sir.
है ना? तो उस क्वेश्चन को देखें. So now you can see किस तरह से हम प्रॉब्लम को. So what is main challenge? Main challenge is that you have to know what is your delta k and what is your k. K is that nothing but the energy. You have energy here, and what is your delta k. So once you know what is your delta k, and this is experimentally founded, this delta k can be found experimentally in general. Okay, and in general we are just talking about all possible L. So this is just for the all possible L. Okay, so L is equal to 0, L is equal to 1, something like this. So let's go for one problem which asked in your exam. So now you have to only use this formula, but you have to understand what is this complete physics behind that. यहाँ तक clear है? Because एक बार मिटाऊंगा तो फिर मुश्किल हो जाएगा. Are you getting this thing?
सर
बोलो.
सर ये जो फॉर्मूला है वो सारे किस के लिए वैलिड है, लाइक हाई एनर्जी, लो एनर्जी?
यहाँ तो हमने एनर्जी का तो कुछ कंसिडरेशन किया नहीं है ना? बट इन जनरल देखो, व्हाट इज मीनिंग ऑफ हाई एनर्जी एंड लो एनर्जी? If you are talking about low energy, then L will be 0 or 1 maximum. Okay. And if you are talking about high energy, then L can be all possible values. समझ रहे हो मैं क्या कह रहा हूँ?
Yes, sir.
है ना? So उसके बारे में बात करेंगे. We will solve one problem, then you can see. Yes, this is true for high and low, both type of energy in general. But yes, आपको high energy के लिए extra calculation करना पड़ेगा. But for the low energy, yes, it will give you very nice answer. और हम अभी देखेंगे भी एक प्रॉब्लम में. लेकिन पहले जो एग्जाम में आया हुआ था प्रॉब्लम, वो देख ले. So विश्वास ने भेजा था मुझे, है ना? Okay. So phase shift of 30 degree. Okay. So what is delta? Delta, let's say 1 is given for 30 degree. Is observed for a beam particle of energy. So let's say that time energy is 0.1 mega electron volt. Okay. Is scattered by target when beam energy is changed and observed phase shift is 60 degree. So let's say now new delta is 60 degree. So this is 60 degree. Assume there is only S wave scattering. What is meaning of S wave scattering? Meaning of S wave scattering, that means we have to only talking about L is equal to 0, isn't it?
Yes, sir.
है ना? So what you have to do, you have to calculate E2. What will be E2? अब बताओ हो जाएगा ये?
Yes, sir.
है ना? अब फर्स्ट वाले में क्या लिखेंगे? सिग्मा 1, है ना? and cross section doesn't change. ये साफ लब लिखा हुआ है, cross section doesn't change. That means you have to write 4 pi upon k1 square. L is equal to 0. That means sine square 30 must be equal to 4 pi upon k2 square sine square 60. Mainly we have to calculate k2, isn't it? So this 4 pi is cancelled, and you can write k2 square, and that k2 square is sine square 60 plus sine square 30 k1 square. यही तो निकालना है. And what is k2? Basically, let's say 2me upon h cat square is equal to sine square 60 upon sine square 30, and this is E2, and 2m E1 upon h cat square. So 2m h cat square is cancel out. You can easily calculate E2. मिल जाएगा क्या?
Yes, sir.
है ना? E2 की वैल्यू कितनी? साइन स्क्वायर 60 कितना होता है? √3/2.
3/4.
This is 3/4. Okay. And this is what? 1/4.
1/4.
और ये कितना दिया हुआ है? 0.1. सो ये कैंसिल हो जाएगा. है क्या 0.3 मेगा इलेक्ट्रॉन वोल्ट टाइप से कुछ?
Yes, sir. Option B.
ओके. So you can just use this thing. ठीक है? ओके. सो यू कैन सी. तो आपको सारा चीज दिया रहेगा, ओनली आपको ये फॉर्मूला को ढंग से यूज करना है. ऑब्वियसली इतने ज्यादा डीप में तो कोई आपसे पूछने नहीं जा रहा है ना? बट यस, एक बार आप पढ़ लियो तो अच्छे से पढ़ लो, है ना? और चलो एक और प्रॉब्लम करें. टाइम है हमारे पास? हाँ, एक प्रॉब्लम करते हैं, मे बी एग्जाम में आ जाए, क्योंकि सिंपल प्रॉब्लम है. आई थिंक अब स्कैटरिंग के सारे क्वेश्चन हो गए होंगे, है ना?
सर असाइनमेंट में भी एक एस वेव वाला क्वेश्चन था सर, यही है क्या?
अब क्या पता यार, मुझे उतना याद नहीं रहता है. देख लो, कॉन्सेप्ट यही होगा. ठीक है. सो लेट्स गो फॉर नाउ. अभी तक हम लोगों ने देखा था हार्ड पोटेंशियल, हार्ड स्फीयर को किया था, कितना टफ कैलकुलेशन आ गया था. रिमेंबर दैट थिंग? टोटल स्कैटरिंग क्रॉस सेक्शन के लिए. So let us go for VR is equal to infinity, R is less than A, is equal to 0, R is greater than A. Now we have to calculate basically our scattering cross section. Okay, we have to calculate, and this is hard sphere. So what we can do? We have the total scattering cross section into this region as, I can write A sine, and we can write this thing as KR plus delta L, because there is some, what will be wave function into this region? बताइए, what will be wave function into this region? साइन या कॉस के फंक्शन में होगा, है ना? और r is equal to a पर उसे डिके करना होगा. So why we have just taken something like sine wave function हमने लिया है, and this delta L is your basically, and this is in region r is greater than a, and this is your phase shift. अगर एक्सपोनेंशियल में लिखोगे तो 2i delta kr, 2i delta L लिखेंगे, otherwise delta L से हमारा काम चल जाएगा. So now what will happen? So if so this will, and what will be region 2? What is wave function in region 2? that is 0,
0.
है ना? So this is 0. So what will happen? So this term A sin KR or KA plus delta L must be equal to 0,
Yes, sir.
है ना? So from here you can have this particular thing. KA की वैल्यू मिल जाएगी, है ना? या डेल्टा L की वैल्यू मिल जाएगी. What is delta L? You can put और साइन को ओपन कर लो तो क्या हो जाएगा ये?
n पाई के बराबर होगा.
साइन KA into cos delta L plus cos KA into sin delta L must be equal to 0. और यहां से आप सॉल्व करोगे, then KA is equal to delta L. Mainly we have to talk about mod value. So we can have KA is equal to delta L. है ना? And for the low value of energy, delta L is equal to what? L is equal to 0 हम पुट कर सकते हैं, है ना? Low value of energy for L is equal to 0. So what is my sigma? My sigma is 4 pi K square and summation over 2L plus 1, and you have sin square delta L, or delta K, delta L is same thing.
Sir, K is equals to minus delta L.
हाँ, ठीक है, but we are taking the mod value ना, because everything is in the area. Okay? Clear है ये?
Yes, sir.
You have to take the mod value of this. Don't worry. Because हमें पता है ये area के term में आना है ना? So nothing to do with this. So this is 4 pi, and for low value of energy L is equal to 0. So 4 pi KL, and this value is what? 0. है ना? And what is this? This is sin square KA. Okay? And for the low value of energy, we can put KA square here and KA square. So for low value of energy, the energy is small, then I can assume that this value is equal to what? 1. So what is sigma here? So sigma is nothing, 4 pi A square. This is all about your scattering cross section for a sphere, and this is for the low value of energy. So now आपने क्लासिकल स्कैटरिंग देखा था. क्लासिकल स्कैटरिंग कितना था?
पाई बी स्क्वायर,
पाई ए स्क्वायर, है ना? एंड दिस इज लो वैल्यू क्वांटम मैकेनिकल स्कैटरिंग. So this is 4 pi A square. So what will happen? Effective area बढ़ जा रहा है क्लासिकल से. Why? क्लासिकल से effective area बढ़ जा रहा है. Why it is that? बोलिए. What is going to happen? जिसके कारण ये एरिया बढ़ जा रहा है. बताओ. इतना तो पढ़ाई कर लिया. Due to superposition of wave. Are you getting this thing? So classical में क्या हो रहा है? एक particle आया, and you have some particle and you have same trajectory and you are just getting this thing. But what will happen in a quantum mechanical thing, when you have wave function and it is going to superimpose to each other after scattering. So when it is going to superimpose each other, the effective area, effective cross section will increase for low value of energy. What will happen to high value of energy? That will be between these two or more than this or less than this. बताइए क्या होना चाहिए? इन दोनों के बीच में होना चाहिए. दिस इज योर लो वैल्यू क्वांटम मैकेनिकल स्कैटरिंग, है ना?
बीच में
इन दोनों के बीच होना चाहिए या इससे ज्यादा होना चाहिए, इससे कम होना चाहिए? बताओ. Obviously, that should be in between this two. Why? Because if particle is coming very high energy, then chance of superposition is very less. It will just penetrate and go, just like little bit of classical thing. But yes, there is superposition. So why it is more than classical, but less than low value quantum mechanics. And you will surprise that this value is 2 pi a square. So let us go and calculate this one also.
सर सर इसमें जो हम लोगों ने वेव फंक्शन लिया r ग्रेटर देन a के लिए, तो ये हमने अज्यूम करके लिया था या क्वेश्चन में दिया हुआ था?
नहीं हमने लिया है ये.
तो सर
भाई जहां पर फंक्शन, भाई आपका वेव फंक्शन क्या होगा, साइन या कॉस ही तो होगा जहां पर पोटेंशियल जीरो है. तो
यस सर.
या तो फिर e टू द पावर i के r के टर्म में कर लो, है ना.
यस सर.
वो भी तुम्हारा यही देगा, है ना.
ओके सर. यस सर.
ठीक है. और जो पोटेंशियल का रीजन वो इतना छोटा है कि उसको हम नेग्लेक्ट कर सकते हैं, इसी कारण साइन ले रहे हैं, बिकॉज दिस हैव टू अल्टीमेटली डीके. आर यू गेटिंग?
यस सर.
अब आप देख रहे हो ये जो आपका पोटेंशियल का रीजन है वो बहुत छोटा है, एंड दिस इज ऑल स्पेस. सो आप एज्यूम कर सकते हो कि ओके, आई कैन टेक ऑल थिंग एज सेम. दिस इज शॉर्ट रेंज पोटेंशियल के लिए पॉसिबल. अगर बिग रेंज पोटेंशियल है, देन इट विल क्रिएट अ हैवॉक. सो इट इज assumption that this potential has effect just about its neighborhood. So this is one of the most important assumption all the theory whatever we have done. ठीक है. Okay, so let's go for high energy value. So for high energy value,
सर
हाँ बताओ.
सर ये जो 2 वाला फैक्टर था वो मतलब e टू द पावर में, सर इसमें तो नहीं लिया, फिर भी मतलब सेम ही रिजल्ट आएगा क्या?
क्या बोल रहे हो? 2 वाला फैक्टर नहीं लिया?
सर ये जो सर साइन के r,
हाँ, उससे कोई खास फर्क नहीं पड़ रहा है, बिकॉज आप तो फाइनली ये ले रहे हो ना.
यस सर.
और जब आप एक्सपोनेंशियल वाला पार्ट ले रहे हो तो वहां 2 का फैक्टर ले रहे हो ताकि साइन का पार्ट डेल्टा एल आ जाए. ओके,
ओके सर.
है ना. जब आप पूरे डेरिवेशन को देखो तो 2 का फैक्टर क्यों लिया है? क्योंकि यहां पर आपको साइन डेल्टा एल आ जाए, है ना. तो अगर आप साइन और कॉस्ट के टर्म में लेते तो फिर आप डेल्टा एल ही लेते, लेकिन एक्सपोनेंशियल वाले टर्म में ले रहे हो इसलिए 2 ले रहे हो ताकि वो साइन डेल्टा एल में आ जाए. तो अगर साइन में लेते हो तो आपको डेल्टा एल में काम चल जाएगा. ठीक है. So actually your phase shift is delta L and 2 is due to your mathematical compulsion, ताकि आप चीजों को डेल्टा L के टर्म में लिखो, ना कि डेल्टा L by 2 के टर्म में लिखो. Are you getting my point?
यस सर.
So what is 4 pi upon k square, and this will be 2L plus 1, and there is sine square delta L or delta k. So what will happen? Now all the possible L will be there. All the possible L. So L will be go to 0 to 2L plus, sorry, 0 to L maximum. All possible L. And we can take the average value of this. So what will be this sine square average value of some angle? Half.
हाफ.
है ना. All possible angle के लिए इसको आप कर रहे हो. So that will be 4 pi upon k square into 1 upon half. And now you have 2L plus 1, L is equal to 0 to L maximum. Okay. So what will be this summation? हम लोगों ने कहीं तो किया है ऐसा summation? बताओ, कहीं किया है ऐसा summation?
2n square शायद, n square.
N square, है ना. So this value is nothing but what? Equal to n plus 1 square, not n square, n plus 1 square. याद है यहाँ n minus 1 तक जाते थे तो ये n square आता था, याद है हाइड्रोजन एटम में.
यस.
2L plus 1, if we are going 0 to n minus 1, then this value is n square. Remember this thing? So what is this value? So this value is 4 pi k square 1 by 2 into n square. So what will be n square? L maximum plus 1 whole square. So L maximum is very, very high than 1. So you can also write it comparable to more or less. For the high value of energy, we can write 4 pi upon k square into 1 upon 2. And here you can just go for L maximum square, just for the convenience. Otherwise, this is your answer. What is your L maximum actually? What is your L maximum? L is nothing but the angular momentum. Okay. What is your L maximum? If you are taking your maximum value of L, what is this particular thing? That value is 4 pi k square into 1 by 2 into, I can put L maximum is nothing but equal to Ka, and this is all square. So we have this value as 2 pi a square. And now you can see this is less than low value of energy, 2 pi a square. Okay. This is your L maximum. L maximum is equivalent to Ka. So you can just use this result. Itna derivation to nahi aayega, but sometime they can ask you, mainly in GATE exam, what will happen to low energy, what will happen to high energy. So this is your 2 pi a square. ठीक है? So I think this is more than enough. अब इससे ज़्यादा जाएंगे तो it will create havoc. But if you will go for your previous year question, either from NET or GATE, और दूसरे एग्जाम में तो उतना आता नहीं है. आई थिंक एक बार जेस्ट के एग्जाम में आ चुका है क्वेश्चन, वो भी हम लोगों ने किया है उसी तरह के क्वेश्चन, है ना, जिसमें इम्पैक्ट पैरामीटर के टर्म में मिनिमम डिस्टेंस को लिखना है. हो जाएगा ये क्लासिकल स्कैटरिंग को ध्यान में रखते हुए, है ना. सो कंजर्वेशन ऑफ एंगुलर मोमेंटम, कंजर्वेशन ऑफ एनर्जी, ये दोनों को यूज करके आप इजिली कर सकते हो. सो डोंट वरी, मेनली व्हाट यू हैव टू डू, मेनली यू हैव टू go for bond approximation for the examination point of view. Bond approximation को काफी अच्छे से करो, and then this formula का use आप देख सकते हो. ठीक है. More than this, इसके अलावा मुझे नहीं लग रहा है कि कुछ आपके एग्जाम में टच करने की जरूरत है. ठीक है. मैं चाहता तो जस्ट फॉर्मूला लिख के भी काम चला सकता था, बट उसमें उतना मजा नहीं आएगा, है ना. बट आप फॉर्मूला को ध्यान में रखो. 2 formula for the bond approximation. One is a spherical polar coordinate for high energy, another is low energy for any type of coordinate, है ना. So you have just a spherical symmetry for high energy, and low energy के लिए है आपके पास formula. That is one formula, and one formula is this one. This is also known as optical formula. ठीक है. So this thing, and इसके अंदर की जो फिजिक्स है वो तो हम लोगों ने काफी ज्यादा डिटेल आंसर कर रखा है. Okay. Any more doubt?